Hi everyone, thank you for attending my presentation. My name is Miguel Mosteiro. This is joint work with Dariusz Kowalski. The leader election problem is fundamental in distributed computing for breaking symmetry. And in networks in particular, it can be defined simply as given a system of n nodes, select a unique node to adopt a role. There are some variants of leader election depending on whether all the nodes know the leader or not, whether the decision on the leader is final or it could be changed later, and whether the nodes know the network size or not. In our model of ad hoc network, we consider a static connected network, and we assume that nodes do not have identifiers or labels. We only assume that links have port numbers. And we consider, in our static, we consider known and unknown network size. We assume that the communication is synchronous. In each round, a node broadcasts a message to all neighbors and receives a message from all neighbors, and that the communication is carried out in the congest model. That is, in each round and in each link, only big O of log n bits are allowed to be transmitted. Our performance metric is time and message complexity to consider energy-constrained scenarios. For deterministic leader election algorithms, it was shown that it's not possible in anonymous networks in the 80s, so we focus on randomized leader election in two scenarios: known network size, where we present an algorithm and prove bounds on time and message complexity, and unknown network size, where we show that no randomized algorithm stops, not even with constant probability. Therefore, we focus on a variant of the leader election problem that we call revocable leader election, and we present an algorithm that works in such a scenario, and we prove the time and message complexity bounds. With respect to previous work, the closest work to this one is by Gilbert et al. In 2018, and our bounds are better in time and message complexity for scenarios where the inverse of the conductance is upper bounded by small o of t mix divided by log n, which is pretty reasonable given that the known bounds on mixing time of 1 divided by conductance square and 1 divided by conductance. Otherwise, our bounds are only larger by a logarithmic or polylogarithmic factor. Our bounds are also nearly optimal for networks with a reasonable expansion, mixing time in the order of 1 divided by conductance, leaving only a gap of 1 divided by conductance to the 1/4 with respect to the best known lower bound, which is existential, also due to Gilbert et al. For unknown network size, we show that no algorithm stops even with constant probability, and we present an algorithm that solves the revocable leader election problem, meaning that the decision on the leader may change in the future. And this version of leader election is our algorithm achieves explicit leader election. All nodes get to know which is the leader. I'm going to overview now quickly the leader election algorithm for known network size. In the first step, each node chooses an ID at random with probability function of n such that all nodes get a unique ID with high probability. In the second step, each node chooses to be a candidate for leader at random, also with probability function of n, so that we have a logarithmic number of candidates in the whole network with high probability. Next, each candidate node spans a territory tree by a method that we call cautious broadcast that expands the tree only in less populated branches. More details soon. In the fourth step, each candidate probes its territory by multiple lazy random walks, and the larger ID, source ID, wins, meaning that nodes keep updating their source ID that they have to the largest. And in the last step, nodes in the territories converge cast the largest ID that they have received to the candidate node. Our analysis shows that candidates with this procedure learn the IDs of other candidates, and the candidate that does not receive any larger ID becomes the leader, all with high probability. The cautious broadcast method has the following ingredients. In general, the idea is the candidate spans a tree broadcasting its ID, but we want to save messages. So tree nodes choose new neighbors at random to expand the tree, but only if they are in sparse branches. How do we figure out that? Well, tree nodes maintain the structure of the tree, parent and children port numbers, and the number of nodes in their subtree, and their status of whether they are extending or not the tree, and the candidate controls the size of the tree by activating or deactivating the expansion using this information. This is a novel algorithm. For revocable leader election, we present an algorithm that we call blind leader election with certificates via diffusion with thresholds, and the key ingredients are the following. Iteratively, nodes use as an estimate of the network size, which will allow them to, at the end, choose an ID and decide the leader with that ID. The estimate is increased in powers of 2, 1, 2, 4, 8, and so on. We call that variable k. Then for each iteration, the algorithm has two phases, certification and decision. In the certification, nodes check whether k is still too low to choose an ID. And in the decision phase, each node that did not choose ID yet and did not detect k as low chooses an ID and stores k as the certificate. Then updates in each iteration of the outer loop, updates this information whenever they receive either a larger certificate or the same certificate with a smaller ID. Our analysis shows that some node will not choose ID until the estimate is large enough, and we use the estimate, that is, we use the estimate as a certificate of uniqueness. For open questions, the natural open question is to remove the knowledge of conductance and mixing time from the known N algorithm, improve the upper and lower bounds for both because there are still gaps, and consider asynchronous protocols. Any questions?